Hello, I will introduce our framework AMD. It is an autoregressive motion diffusion model, which aims to produce plausible human motion sequences according to various conditional inputs, such as text or audio. Human motion refers to the movement of the human body and its parts. Humans plan and execute body motions based on their intention and the environmental stimulus. Human motion generation is a crucial task in computer animation and has applications in various fields including gaming, robots, and film. The goal of human motion generation is to generate natural, realistic, and diverse human motions. Traditionally, new motion is accessed through motion capture in the gaming industry, which can be costly. With advancements in generative model technologies, there has emerged a series of studies in human motion generation based on text and audio inputs. These methods autonomously generate natural, realistic, and diverse human motions by analyzing text or audio data, circumventing the need for expensive motion capture setups. Despite the progress made by existing methods, text-based conditional human motion generation remains a challenging task for several reasons. 1. Lack of enough motion data. At present, there are few widely used text-to-motion datasets, such as Human ML3D Babel KitML, which mostly contain simple motions and are deficient in long text prompts, i.e., he is flying kick with his left leg. 2. Weak correlation. Due to the differing distributions of language and human motion, resulting in a multiple mapping problem. This issue is further exacerbated when generating long text-based human motions. To address the aforementioned limitations and challenges, we propose Autoregressive Motion Diffusion Model, AMD, that can generate motion sequences with complex long content, variable duration, and multiple modalities. Considering the high dimensionality of complex long motion sequences, in order to better capture the dependencies between texts and motions in long sequences, AMD combines the text description at the current time step with the text description and motion information at the previous time step as conditional information to predict the motion sequence. Especially given the current text prompt, the last text prompt, and last motion, green arrow, we first encode the context information, blue block. Then, we feed the input conditions and corrupted motion to AMD module to generate the original cleaned motion. Afterward, we send the current text prompt and motion to the next time step. Iteratively, we can obtain motion sequences for long text prompts. For the AMD module, the denoising process, gray, and the diffusion process, yellow, span a total of t time steps, where t represents the predefined maximum time scale. We directly predict the original cleaning motion clips during the denoising process, while the diffusion process operates in the opposite direction. We conducted a series of quantitative experiments. These are the human motion results generated by AMD driver under long text prompt. We conduct compound motion generation with SOTA methods. Since the Human ML3D dataset does not contain motion coherence information, we conducted this experiment on the Human Long 3D dataset. Additionally, we designed 3 benchmark 1, joint prediction RSJ. A long semantic prompt formed by the combination of 2 coherent prompts are used as the input of the diffusion model, and a coherent time series motion sequence is obtained by direct joint prediction. 2. Linear interpolation RSI. This method interpolates the results of 2 independent motion synthesis. 3. Motion filling RSF. Similar to linear interpolation, 2 independent motion synthesis are required to obtain, and the time window is set to 10% of the motion sequence duration. All frame data except for the time window are fixed, and the frame data within the time window are filled with random normal distribution noise. The coherent motion sequence is then restored through the denoising process. Compared to the ground truth, AMD keeps with the highest degree of similarity, while MDM, motion diffuse, and MLD all exhibited varying degrees of limb stiffness. Although T2M-GPT achieves results comparable to the ground truth in the first half of motion generation, its performance deteriorates in longer text-to-motion generation tasks. This is due to its premature prediction of the terminator, resulting in a lack of corresponding motion sequences for the second half of the text. For T2M-GPT, we also tried to separate the long texts into short texts and generated single motion on the short texts individually. T2M-GPT performs well in single motion generation tasks but struggles with compound motion generation tasks. Additionally, when generating long text to compound motion, dividing the long text and generating it separately often results in unnatural transitional motion clips. Among the 5 evaluation metrics, AMD achieved top 3 performance in 4 of them, with FID and diversity, the primary metrics for motion generation quality, ranking first, demonstrating its superiority in the long text-to-compound motion generation task. Notably, AMD outperformed other methods by a significant margin in the FID metric, while the AAAI scheme, despite having the highest multimodality index, performed poorly in terms of FID, indicating its inability to generate reasonable human movements. In cases where synthesis quality is extremely low, high diversity in multimodality may indicate that the synthesized actions are chaotic and irregular. We also conduct single motion generation experiments on human ML3D and human long 3D dataset. For single motion generation, our conditional information includes the estimated motion duration and semantic information, but excludes prior motion and semantic information. It can be seen that AMD is capable of generating corresponding motion in response to text prompts containing a single motion while achieving smooth transitions. We also conduct music-to-dance experiments on human music and ICE++ dataset.
이런 내 맘 거울에 들킬까봐 그려본 내 입술은 혼자가 편해.
It can be seen that AMD is capable of generating corresponding motion in response to the music signal, realizing X to motion with no modality left behind. Thanks for your attention.